mutual RCS interactions between different nearby targets. Next slide, please. Okay. So the last two slides show you time domain screen captures. So FDDT uses Maxwell's equations directly in the time domain, and it calculates electromagnetic scattering effect in the time domain. But RCS is defined for single frequency, which means RCS is defined in the frequency domain. So if you use FDDT, you need to follow these three steps in RCS modeling. First, you run FDDT in the time domain and record time domain scattering transient effects. Then you run fast Fourier transform or discrete Fourier transform with the recorded time domain data and get the RCS in the frequency domain. And in that step, you plot RCS versus angle or RCS versus frequency. So this is the target F16, and you observe four polar plots. The first one on the left top belongs to 60 megahertz, where L is equal to 3 lambda. So L is the length of the F16, it's 15 meters. Then the radar signal is coming from the 0 degrees. So this is the first one belongs to side illumination. On the B, the second one on the top, you change the radar angle and then observe electromagnetic scattering RCS around the object. C belongs to 1.2 gigahertz, where L is equal to 60 lambda, and D belongs to the same frequency, but for different angle of illumination, angle of radar signal. So the top ones belong to 60 megahertz, the bottom ones belongs to 1.2 gigahertz. So the top belongs to resonance RCS regime, but the bottom belongs to optical RCS regime. And for each one, the first important thing for the RCS engineer is that whatever the frequency or angle of illumination are, it doesn't matter. The strongest contribution, the RCS contribution, is the forward scattered component. You see, the forward scatter is always dominant in RCS engineering. Next slide, please. Here you see two different aircrafts, F-117 on the left, which belongs to the red curve, and the blue curve is B-29 bomber. So the left one is a low visible target, but the right one is a high visible target. The RCS of F-117 is much smaller than B-29 on the left. There is almost 20 dB difference between the red curve and blue curve. But on the left, theta is 90 degrees and phi is 90 degrees, which means the radar is coming from the nose of the aircraft. But on the right, theta is chosen as 30 degrees and phi is 0 degrees. These two angles correspond to quite top illumination. So if you observe these two targets from the bottom or top, their RCS is almost are almost in the same order. So although the left one is low visible target, depending on the radar direction, the angle of illumination, you can still catch or capture or observe, detect these targets with your radar systems. So the angle of illumination, the angle of the radar is critical in RCS measurements or radar systems. Next slide, please. Another example where DC-10 is used for two different angle of illuminations. So once you write down your package, once your package is ready, or once your FTDT is ready, you can select any parameters. You can change frequency, you can change angle of illumination, you can change the target, and get these results. So these results are very important in training both RCS radar engineers as well as the pilots, the aircraft fighter pilots. Next slide, please. Okay, so here you see two aircrafts, two F-16. On top, they fly one on top of the other, and at the bottom, they fly side by side. So one beauty of the numerical packages is that you can play with them with what-if type games. What if I have two aircrafts? What if they fly side by side? What if they fly one on top of the other? So these are critical in detecting. If you are a radar engineer, you need to play these kinds of games and train your radar operators to capture enemies' targets. If you are an aircraft pilot, you also need to play these games and train your pilots in order to avoid being captured by enemy radars. So numerical models are very effective in playing these what-if type games. Next slide, please. Okay, here you see RCS versus frequency. The vertical axis is RCS in dB, and horizontal axis is the frequency, and it starts from 0 frequency to 100 megahertz. We have two curves. The red one belongs to one F-16, and the blue one belongs to two F-16, as they are flying side by side, and the radar signal is also given on the figure inset. So the red one belongs to single F-16, but the dashed blue curve gives you two RCS for two F-16 flying side by side. As you see, as the frequency changes, at some frequencies, single F-16, single target RCS is more than double target RCS. But at other frequencies, double target gives you stronger RCS contribution. So this slide shows you the complexity of the RCS computations and measurements. It depends on the geometry of the target. It depends on the number of targets. It depends on their locations. It depends on the distance between targets. It depends on angle of illumination, radar signal, the arrival of the radar signal. It depends on the frequency. So RCS engineers need to measure or do the simulations at every single frequency. It is almost impossible to predict, for example, high frequency RCS behaviors from low frequency ones. So you cannot say, okay, at low frequencies, these two targets give me this type of RCS. If I increase the frequency, I can expect this type of RCS change. It is almost impossible to do this prediction. So RCS simulations and RCS measurements must be performed at every single frequency because the scattering phenomenon, electromagnetic scattering phenomenon, is very complex. It is not easy to predict from a few measurements the others. Next slide, please. Okay, so I think we should give a break at this point. And then in the second part, we are going to focus on the real subject, real topic, electromagnetic diffraction modeling and simulation.
Yeah, that's nice. So we can have a break, dear participants, and we can resume back another 20 minutes by 11:20. Is that fine, Professor Sevgi?
Yes, yes.
Yeah.
That would be perfect.
We'll have a 20 minutes break and we will just get back to the same session where Professor Sevgi will be continuing on EM diffraction modeling and simulation. Attendees, hope you have the link, and there is also a Telegram channel which you can join, and I have already shared the link in the chat, and the more updates on CONECCT will be told in that. And let's all meet back at 11:20 back and with the same WebEx link what was given to you. You can use the same link and join back. Thank you.
Okay, thank you.
And dear participants, if you have any questions, you can always leave on the chat window, on Q&A window, which will be addressed by our speaker at the end of the session. The last 15 minutes of the session will be for Q&A. So any questions, you can always jot down or you can type down on the chat window, as you people have only the audio thing and you cannot talk on one-on-one because of the distraction. So make sure any questions you can type on the chat window and that will be addressed by our speaker.
Thank you. Welcome again. In the second part, we are going to focus on electromagnetic diffraction modeling and simulation. Next slide, please. So here you see how light is also electromagnetic waves. So some diffracted lights, different pictures from different times of a day, diffracted from the edge of a roof, or diffraction from the tree, from the leaves, from the branches, etc. So diffraction is very critical in antenna engineering, in propagation engineering, in radar engineering, and in RCS engineering, which we prefer to call all of them electromagnetic engineering. So tomorrow I will have a keynote talk, half an hour long, about electromagnetic engineering, how we have transformed from engineering electromagnetics almost 30 years ago today to electromagnetic engineering. So electromagnetic waves are everywhere. So we need to well understand Maxwell's equations. We need to well understand scattering effects, which means target and or object and electromagnetic wave introduction. Next slide, please. Okay. There's a video. Unfortunately, we cannot see it, but let me tell you a few things about electromagnetic scattering. So electromagnetic waves interact with objects, including us human beings, and scatter. So the word scatter includes every possible electromagnetic effect. So we prefer to call electromagnetic scattering to cover every electromagnetic effect from this interaction. But basically, scattering includes reflection, refraction, and diffraction. We also have some other traveling waves, surface waves, whispering color waves, but basically we deal with, as an electromagnetic engineer, we deal with reflection, refraction, and diffraction. As we will see in the next few slides, edges and tips cause diffraction. Edge means the interaction of two planes. The joint of two planes is called edge. Tip is the geometrical point of the intersection of three planes. So sharp edges and tips, also smooth ones, they cause diffraction, and we will see in the second part how we mathematically model them and how we numerically model and simulate them. So if you send an electromagnetic waves onto an object, that electromagnetic wave interacts with the object. And from this interaction, surface currents or volume currents are created on and in the object. So we call them source-induced currents. They act as secondary electromagnetic sources. And these source-induced currents can be divided into two: uniform currents and non-uniform currents. So non-uniform surface currents excite diffractive fields, which we also call them fringe fields. Next slide, please. So this is a screen capture from a simple two-dimensional FDTT space. The red circle on the left bottom is the source location, is the source. And the source is a continuous wave source, which means a single frequency source. And you see different wave phenomena there. One represents the propagating wave, the outgoing cylindrical wave in two-dimensional space. Two, in the region 2, you see the interference of the propagating and ground reflected waves. So there is the interference. So direct and ground reflected waves interfere. If their phases are equal, they form maximum contribution. If their phases are opposite, they cancel each other. The region 3 represents the multi-reflection region. In region 4, between two square objects, you see, if you put your receiver in region 4, you cannot see the transmitter. So there is no reflection, direct wave, and refraction, but there's only diffraction in region 4 and also behind on the right of the other objects also. Observe the tip of the small object, the right up tip of the object. You see, there is a kind of cylindrical wave from the tip with the colors light blue and yellow. So that one is the tip diffracted wave. It seems that as if we put another transmitter there. So tips and edges, they create secondary sources, basically from the effects of diffraction. So we will see how we get them and how we can compute them and how we can simulate them. Next slide, please. Okay. Different shapes with different sharp edges and knife tips cause electromagnetic diffractions. So smooth surfaces or plane type surfaces, they create reflections. If the object is transparent, then or penetrable, then we have refractions. If we have edges and tips, we have diffractions. And in most of the communication links, for example, for our cell phones, the antenna of our cell phone cannot usually see directly the antenna of the base station. So there is no direct wave, there is no reflections, but basically the communication link between your cell phone and base station antenna is established because of the diffracted phase. Basically, diffraction establishes links in shadow regions. Next slide, please. We need to skip this one because these are video captures showing some effects of the diffractions, but we cannot see them for this online presentation. So next slide, please. Also, next slide, please. I wish I could show you these video captures, but here. So we have, this is a scenario where we have finite length, infinite metal strip, and with different boundary conditions. SBC means a soft boundary condition, HBC means hard boundary conditions. And in electromagnetics, they correspond to transverse electric and transverse magnetic TE and TM type electromagnetic waves. So on the left, you see the incident field, On the middle, you see scattered fields, and on the right, you see the total fields in front of and behind the metal strip. Next slide, please. If you change the direction of the radar signal, you get this type of illumination. Again, on the left, we have incident field. In the middle, we have scattered fields, and on the right, the total fields. So, if you are an antenna, if you are an RCS engineer, you basically focus on the middle ones, the scattered fields. But if you are an antenna engineer, you focus on the total fields. So antenna engineers basically deal with total fields, but RCS engineers basically deal with scattered fields. So incident field plus scattered fields gives you the total fields. Next slide, please. Okay, this is another example. I wish I could show you the video clips. Next slide. So let's skip this one also. This one also. Okay. So the first part, we focus on scattering with macro scales, which means we deal with air targets and RCS modeling as a whole. Now we go to micro scale, and we are going to see diffraction modeling and simulation. So we will focus on the physical understanding and mathematical foundation of microscale diffraction modeling. Next slide, please. Okay. As I said in the last few slides, electromagnetic waves interact with objects and scatter. But the word scattering is general. It includes every electromagnetic phenomenon, like reflection, refraction, and diffraction. In early times, we used geometrical optics, and GO describes a wave field in the limiting case when a wavelength tends to 0. So if the wavelength is almost 0, which means the frequency is very high, almost infinite. That's why we call GO as a high-frequency asymptotic method. So GO deals with reflection and diffraction on the illuminated side of objects and cannot take into account the diffracted fields. So geometrical optics, GO model or approach, gives you electromagnetic effects, basically reflection and diffraction on the illuminated side. According to GO, the field in the shadow region behind the object is equal to 0, and on the illuminated side of the object, GO field is the sum of the incident and reflected fields. Next slide, please. Diffraction was first mentioned by Grimaldi in 1665, around 1665. So, according to Grimaldi, diffraction of waves is any deviation in their behavior from laws of GO, geometrical optics. A diffraction is a phenomenon which cannot be taken into account by GO, geometrical optics. There are two commonly used approaches in the high-frequency asymptotic theory of diffraction: the ray-based and induced source-based techniques. The first one, the ray-based technique, is called geometric optics and geometrical theory of diffraction, GTD. So if you use geometrical optics and rays, then you call it GTD, geometrical theory of diffraction. The second one, which was founded by the professor I mentioned to you in the first part of the Ufumsev. It's called the physical optics, PO, and its diffracted version is the physical theory of diffraction, PTD. So we have two groups, GO and GTD, which are ray-based, and PO and PTD, which are surface or source-induced current-based. So GO and GTD uses rays, but this PO and PTD uses currents on the target or object. Next slide, please. So PTD is based on the fundamental principles of equivalence and localization. According to this principle, a scattered field is considered as radiation generated by equivalent sources induced by an incident wave on an object surface. So you send an electromagnetic wave, it hits the object, it creates some kind of surface currents. Those surface currents act like secondary antennas and they radiate. And these radiations create scattered fields. Next slide, please. J.B. Keller is the founder of GTD. As we will see at the end of this presentation, GTD has some shortcomings, and Uyumcuyan and Patak, they introduced or they extended GTD and call it UTD, Uniform Theory of Diffraction, and they created extended version of UTD. And we will see their advantages, disadvantages, shortcomings, and other properties. Next slide, please. Okay, let's see the wedge problem and understand what diffraction is. So, in two-dimensional space, you see a wedge type geometry here. X is the horizontal direction, Y is the vertical axis, and the top boundary of the wedge is aligned along x-axis. And we have a source on top, which is called line source. It is R0 away from the tip. So we locate the coordinate system on the tip of the wedge. And the angle of the line source is P0. So the point R0, P0 Q represents the location of the source. So if the source has an angle P0 with respect to the top boundary of the wedge, by the way, this wedge is non-penetrable, so we are not dealing with electromagnetic effects inside the wedge because none of the electromagnetic waves penetrate inside. So the wedge problem actually has two different characteristics. The diffracted wedge, as you see on this slide, and we also have wedge-type waveguides where we deal with the effects inside the wedge. That's a different problem. So we only focus on the outside of the wedge in this one. So if you put the line source as on the slide, then you have two boundaries. One is called RSB, reflection shadow boundary, and the other one is called ISB, incident shadow boundary. So according to the location of this line source, RSB is the limiting angle, which is pi minus P0, which divides two regions, with the reflections and without the reflections. And the other one, ISP, incident shadow boundary, with the angle pi plus P0, it divides the region into another two parts with the diffraction and without the, with the incident field and without the incident field. So according to this scenario, we have three regions: region 1, region 2, and region 3. In region 1, we have, if you put your receiver in region 1, you will record incident field, reflected field, and diffracted field. So region 1 includes three wave contributions: incident, reflected, and diffracted fields. But in region 2, we don't have any reflections. So region 2, we have only incident field and diffracted field. In region 3, behind the wedge, we have only diffracted field, because we cannot see the line source, so there is no incident field, and none of the reflected waves can reach behind the object, so we don't have reflections. So we have three regions: region 1, region 2, and region 3. And mathematically, we can use these three regions and separate incident field, reflected field, and diffracted field. So that's why this scenario, the wedge problem, is canonical in understanding in mathematical foundation of diffraction, reflection, and incident fields. So this is basically used in graduate level or PhD level diffraction courses as the canonical structure, where mathematical foundations can be applied, can be taught, and can be understood easily. So remember, we have three regions according to the location of the line source, and region 1, region 2, and region 3. Next slide, please. Now, here's the blue. First, see the blue color drawings. One, the source 1, is the previous slide. If you put the source 1 as in the slide, then reflection and incident shadow boundaries are as I told you on the previous slide. So it is called, the blue one is called single side illumination. So source 1 can only illuminate the top face, the top boundary of the wedge. The second boundary of the wedge is in the shadow region, in the dark region. But if you change the source from 1 to 2, the red ones in this region, your source, the source 2, illuminates both top face and bottom face. Both of the boundaries of the wedge are illuminated. So we have two different scenarios. In scenario 1, the blue one, we call it single side illumination. In the second one, double side illumination. So you start with Maxwell's equations plus boundary conditions, or source 1, and get the mathematical results of reflection, refraction, and diffraction. And then you repeat the same for source 2. You start with the Maxwell's equations or wave equation plus boundary conditions, and do the same for the second scenario. So two different scenarios, but mathematical foundations and the solution approaches are similar. Next slide, please. So this is the wave equation in two-dimensional space and the boundary conditions. And this is how we postulate the problem. Maxwell's equations plus boundary conditions, or as you see here, wave equation plus boundary conditions first gives you the problem, defines you the problem, and then U is the wave function. In electromagnetics, U represents either EZ in TM case or HZ in TE case. And the soft boundary condition OS or hard boundary condition, the normal derivative of OI, OH, 0 on both sides of the wedges. So in acoustic society, they use these two equations. In electromagnetics, we replace U with EZ for transverse magnetic case or HZ for transverse electric case. And in acoustic society, soft boundary condition means TM, hard boundary condition means TE cases. Next slide, please. This is my second book published in 2014, and chapter 10 of this book is devoted to the high-frequency asymptotic methods, the wedge problem. So I'm going to show you a few slides from this chapter. Next slide, please. Okay, analytical solution. The wedge problem with perfectly reflecting boundaries, non-penetrable wedge, has analytical exact solution. We are lucky because this canonical structure has mathematical exact solution. So we have the reference solution. The exact solution may be either in series form, the summation of infinite number of series, or an infinite integral form. In addition to this exact solution, we have ray-based solution, as I said you before, GO and GTD, and the extension of GTD is UTD. So GO, GTD, and UTD are ray-based diffraction theory. PO, PTD, and parabolic equation are induced surface currents-based diffraction models. Next slide, please. Okay. Historically, near almost 100 years ago, they started to establish ray-based and source-based, source-induced current-based diffraction theory with high-frequency asymptotics, with the methods on the previous slides. And when we first started to collaborate with Professor Ufrimsev, we reviewed all of them. We prepared MATLAB codes for all of them, or series summation or integral forms, and we published them in the Antennas and Propagation magazine. Then we published this one, where we use a kind of MATLAB package, and the next slide will show you that package. Next slide, please. Okay, this is the virtual tool or electromagnetic package, which we call WedgeGUI. It's free for IEEE or any people. You can download it from the IEEE site or from our website, or you can send us email. We can send you its latest form because we modified it according to the MATLAB versions. So this is the one screen virtual tool. On the left top, you will supply some of the parameters. For example, wedge angle, incident distance, you locate the source. You choose the boundary conditions, soft or hard. You can select the field type. You may want to visualize total fields or diffracted fields. And the solution types may be exact, PO, PTD, UTD, or parabolic equation. And then you run the virtual tool by pressing the plot buttons. You get the polar plots on the left and rectangular plot on the right. So diffracted fields or total fields around the wedge can be observed on the left plot, and diffracted field versus frequency can be plotted on the right plot. So you can take this one and read the tutorial and understand mathematical details, and then observe how diffracted fields or total fields around wedge occur under different source locations and distances, etc., frequency changes. Next slide, please. This is another video, so we cannot show you this time. So next slide, please. Okay. So in 2012, I organized Mediterranean Microwave Symposium in Istanbul and invited Professor Felsen, the founder of physical theory of diffraction, together with Balanis. Next slide, please. Next slide. So the second keynote invitee was well-known professor, my friend Konstantin Balanis. So Ufimsev spoke about PTD, and Balanis spoke about GTD, and I watched them fighting one another and enjoyed their presentation at that time. Then three of us, Balanis, myself, and Ufimsev, we published a joint paper where we summarized 50 years of high-frequency asymptotes back in 2013. Next slide, please. And this is a paper I mentioned. So it's a nice summary, so you can download it or you can request from me. I can send it to you. Next slide, please. Okay. So we have classical books and well-known famous electromagnetic experts on both geometrical optics, GTD, and physical optics and PTD. Now, the question, since we have powerful computers and very attractive numerical methods like finite time domain FDDT or method of moments or finite element methods, there is the question, can you use those numerical methods and identify or distinguish wave pieces such as scattered field, diffracted field, and fringe field, both in the frequency domain and in the time domain, because we have frequency domain methods like method of moment and finite element method, but the FDDT is time domain method. So is it possible to distinguish diffracted field in the time domain and or in the frequency domain by using powerful numerical techniques? The answer, yes, you can. You can do this by applying either spatial or geometrical superposition principles as well as time dating. So we will see how we do them in the next few slides. Next one. Okay. So chapter 14 of the same book is devoted to finite difference time domain method, and its 14.5 section is devoted to canonical 2D wedge scattering problem. So the next few slides belong to that section from that book. Next slide, please. Okay. So how can we apply a time domain method, finite difference time domain, FDDT method, and get the scattered field as well as the diffracted field? This is in 2D, of course. This is a scenario. So we have XY space, and we have objects in the middle at the center of this computation plane, two-dimensional plane. The red arrow shows the direction of the signal incident field with the polarization, and green dots around the object show you the locations of multiple receivers. So you send a signal from a given direction, and you record electromagnetic waves around the object with dozens of receivers. So your signal, electromagnetic plane wave, but pulse in the time domain, hits the object, and transient effects around the objects occur. Scattered time domain fields around the object occur within a few nanoseconds or picoseconds. Then you record those time domain scattered fields with a number of receivers. So the only equation we use in two-dimensional FDTD in the grid space is also given on the top of this slide. Next slide, please. Oh, here the Ashwin, can you go to the previous? Okay. The computation domain is covered by PML blocks. PML means perfectly matched layer. Since this should be in the free space, there should be no boundaries around the object. So the region should go infinite in all directions. But we have a limited memory and computation space in the numerical model. So we need some kind of termination where we simulate free space. So perfectly matched layers simulate free space. Although they are finite around the object, they simulate free space. So any scattered field going towards the PML blocks are not reflected, so they go to infinity. So the major task of perfectly matched layers is to observe all fields coming into them. Next slide, please. So for the wedge, we put the wedge, we put the source, and the wedge angle may be 60 degrees or 90 degrees. Any angle can be given, and then you start FDDT. These two represent two videos. Unfortunately, I cannot show you. If I were able to show you, then you should have observed incident fields, reflected fields, and diffracted fields around the wedge here. Next slide, please. So if you screen capture at different times during the FTD simulation, you can get the incident field, reflected field, and diffracted field. So these three show you different time instants. The latest one is the front one. So you see the incident field, diffracted field, and reflected field. These are pulses in the time domain. So we send a short pulse to the wedge and record transient time domain effects in the time domain. Short pulse means broad frequency band. So with single FDDT, you can get hundreds of thousands of different frequency behaviors. So you need one FDDT simulation, but you can apply thousands of Fourier transforms, FFT or EFT, and observe diffracted fields in the frequency domain. Next slide, please. So, if you choose one receiver around the wedge, you get this type of time variation. So this is the signal strength. Vertical axis is the signal strength, and horizontal axis is time. So at a chosen receiver, after receiver, first the incident field comes, then the reflected pulse comes. You see, they are pulse in time, and then diffracted pulse comes. So if you time gate incident, reflected, and diffracted pulse, you can separate incident pulse, reflected pulse, and diffracted pulse in the time domain. Then you do Fourier transform, and you get diffracted fields in the frequency domain. So at one single receiver, this is what you observe, signal versus time. So this is the time history of transient scattered fields at a given receiver. Next slide, please. So from that one, you separate them, incident pulse, diffracted pulse, and reflected pulse, and we call it time gating FTDT diffraction method. That was first introduced by Taflov and his colleagues. And the equation on the right, D diffraction coefficient, is given by the ratio of the diffracted time signal versus incident time signal. So diffraction field versus incident field after FFT gives you the diffraction field in two-dimensional space. So this is what we do in order to distinguish diffracted field in the time domain and then get the frequency response. Next slide, please. Go back, please. Go back. Yeah, next one now. This one. Now, unfortunately, for some observation points, it is not possible to observe incident, diffracted, and scattered fields or reflected fields separated in the time domain. But for another receiver, we observe this one. You see this in this one, both incident, reflected, and diffracted fields overlap. So it is not possible to apply time gating. So we introduce another approach, which is a general approach, and we will see them in the next slides. Next one, please. Okay, let's see the method of moments first. This chapter 13 of this book is devoted for method of moments. Also, wedge problem is a section there. The same is also applied for the canonical wedge problem by using method of moments. Next slide, please. So this is the generic scenario of method of moments. You know, method of moments is a semi-analytical, semi-numerical method. You need Green's function solution in order to apply method of moments. So the top equation, U, the scattered field, U, is equal to incident field minus the other term. Inside the integral, you have surface currents induced on this object. So if you drop the point P onto the object, as in the bottom equation, and if you divide the object into small pieces where the surface induced current is assumed constant. You can move the dn term outside the integral and then get rid of the integral. Instead of integral, you replace it with the summation formula. So this is the basic of method of moment. Again, we have an incident field, but in the frequency domain. So this is not a pulse. This is a CV signal. The object is divided into short segments, and on each segment, the source-induced currents are assumed constant. And again, we locate dozens of receivers around this object to record scattered fields. So this is the basic scenario for method of moment-based diffraction modeling. Next slide, please. Okay, this is the generic scenario. We call it multi-step models. Instead of dealing with one single wedge problem, we deal with three different scenarios. On the left, step one is the wedge scenario. We have wedge, incident field, and we record scattered fields around the object. In the second scenario, we replace the wedge with infinite plane one. So the first one has diffraction, or the first scenario, step one has diffraction, but instead of wedge, if you use infinite plane, you have only incident field and reflected fields, no diffraction. And we repeat this one in step three for free space. We remove the object and we just report the incident fields. So in the first step, in the first scenario on the left, we have all components, incident field, reflected field, and diffracted field. In the second scenario, we have only incident field and reflected field, no diffractions. On the right, in the third scenario, we have only incident field. So if we combine all three, we can identify or distinguish incident field, reflected field, and diffracted field. So this is why we call it multi-step FDDT and moment models. Next slide, please. This is another package, another virtual tool where we share this package with the IEEE Antennas and Propagation magazine readers. You can download it and read the tutorial and reproduce the examples there, and then use the package for your own projects. Next slide, please. Next one. This is another video. Unfortunately, we cannot see it. So next slide. Let's skip this one. Okay. So here you see results for incident field at 45 degrees on top of the wedge, and you observe only diffracted fields where you compare exact series, exact results with PTD, UTD, and parallel equation method. So they agree very well. And observe that the major contribution of diffraction comes from those two critical angles, incident shadow boundary and reflection shadow boundary. So the diffraction is very strong along critical angles. Next slide, please. So by running that package, you can create your own scenarios. Here you see total fields on the left plot and diffracted only fields on the right plot. So from the left plot, from the total fields, if you subtract the incident field and reflected field, you get only diffracted fields, as you see on the right one, and with multiple methods, both exact mathematical results. UTD is a high-frequency mathematical approximation, Method of moment is a frequency domain method, and FDDP is a time domain method, and they agree very well. Next slide, please. Another example for different wedge angles and for different angle of incidence. Soft boundary is TM case, hard boundary HPC is TE case. So you can play whatever and get whatever you want from this package. Next slide, please. This is another example. Diffracted only fields, exact results with UTD results. Next slide, please. Okay. The last part belongs to fringe currents, PTD currents. Can you, as we said before, source-induced currents, surface currents, can be divided into uniform, which we call physical optics currents, and non-uniform PTD currents or fringe parts. So you send a signal onto the wedge, and that signal creates surface currents on both sides of faces of the wedge, and we try to divide those currents into uniform and non-uniform parts. So uniform currents appear on planar back surfaces. Non-uniform currents are caused by edge or tip type discontinuities, and uniform currents produce physical optic fields. Non-uniform currents produce PTD diffracted currents, which we call fringe currents and fringe fields. Next slide, please. Okay. Again, multi-step approach to obtain fringe currents and fringe waves is given on this slide. So in the first scenario, we use wedge, and for the single site illumination, we have uniform plus non-uniform currents on the top face, but only non-uniform currents on the below face of the wedge. Then instead of wedge, in step 2, we replace it with infinite plane scenario, and in that case, we don't have tips, we don't have diffractions, only we have uniform currents. So if you subtract one from the other, we discriminate uniform and non-uniform currents. So then we use those uniform currents to generate physical optic fields and non-uniform currents to obtain PTD fields. Next slide, please. This is how we obtain them. JS is the surface currents. So the top current shows you total currents and physical optic currents. If you subtract red one from the blue one, you get the bottom curve, which is only PTD currents. So the left half of this these plots show the currents on the bottom face, and the right side of this plot gives you the currents on the top face of the wedge. So here you see how we discriminate PTD from the total currents. And the next step is easy because you use that as a source and generate fields, diffracted fields. Next slide, please. This is a scenario obtained with the FDDT method with a right angle 90 degrees wedge, hard boundary and soft boundary. Next slide, please. This is another video, so let's skip this one. Next slide. So here you see PTD, MOM, and other methods. There's on the left you see for soft boundary condition wedge, on the right hard boundary condition wedge, and these are fringe currents and fringe waves. Next slide, please. This is, I think, last example where you repeat everything. Analytical methods, exact methods, high-frequency asymptotics, time domain numerical methods, and frequency domain numerical methods. Next slide, please. You can repeat the same for double diffraction. So here you have, instead of wedge with a square type cylinder, where you have two tips, so double diffractions. Next slide, please. These are the results for double tip diffraction. Total fields on the left, yeah, total fields and diffracted fields for different size of rectangular cylinder. Next slide, please. Another one. This is a strip still double diffractions. Another example. So since you have methods, you can create your own methods. Next slide, please. And this is a triangular cylinder, so you have three tips. So triple tip diffraction can also be modeled and simulated with the same approaches. Next slide, please. Okay, now the conclusions. A few slides for the conclusions. Next slide. Okay. We have numerical models and simulators. They have become impressive for both scientific researchers and engineers. Therefore, modeling and simulation and validation, verification, and calibration have become crucial. We need to well understand the physics behind the mathematics and the model of the simulator you use. If available, we need to compare the simulation results with the reference, preferably experimental data. Always keep in mind the assumptions and validity ranges, because most of them are approximate, and check the accuracy. And finally, use TUBIT technologies. In RCS and diffraction, try to look at the object as a whole, but also pay attention to every detail in terms of different electromagnetic phenomena and their contributions. Next slide. High-frequency asymptotic methods have long been used in diffraction modeling. We have GO, GTD. However, GO, GTD, UTD fails near caustics. The PTD supplements PO, and it's more general. Uffenserv suggested the existence of non-uniform fringe currents, edge currents, in addition to the uniform PO surface currents, and we already saw how we extract them. Next slide, please. These are the pros and cons of GO and GTD. It is simple to apply because you plot rays, can be used to solve complicated problems that do not have exact solutions. GO-GTD provides physical insights into the radiation and scattering mechanisms, yields accurate results that compare quite well with measurement of other methods, can be combined with other techniques, and form a hybrid method. Next slide, please. On the other hand, PO-PTD, they provide correctly only the first asymptotic terms for main components of the scattered sphere in 3D problems. So PO-PTD is more general compared to GO-GTD, and is the maximum of what modern asymptotic theories can do for today. It allows constructing relatively simple solutions of practical problems. It provides uniform asymptotics for the scattered field. It clarifies the physical structure of the scattered field, and PO-PTD establish the diffraction limit of reduction of scattering by absorbing coatings, and they can be utilized to develop efficient hybrid techniques. Next slide, please. These are the cons and pros of the numerical techniques, FDD, TOM, and SAM. We have multi-step approach for diffraction theory. But we should note that the diffraction coefficient has a physical meaning only for high frequency fields, which means for when the frequency is very high, where we assume it is infinite. So you need to apply these numerical methods in the limit of high frequency asymptotics. But the critical question is that the real potential and applicability of the numerical methods to fit high frequency asymptotic domain for RCS applications, and how far can one go from the edge. And application of these methods in 2D is not a problem, but it's tricky in 3D, but still applicable. And the intelligent way is to hybridize high frequency asymptotics with numerical models. Next slide, please. This is the scenario with the IEEE APS Lego. We will share this latest version of the diffraction package soon, and you can get it and use with teaching, learning, or research purposes. Next slide, please.
I think these are the end of slides. I cannot move anymore.
Okay, so this is the last one. So this concludes my workshop presentation. If you have time and if you want to ask questions, please do so.
Yeah. So, dear audience, you have any questions, you can always type on the chat window on Q&A window. I have one question here. Is it possible to generate target return signal in multipolarization?
Yes, it is possible. We haven't done it in our examples in our projects, but it's possible. Because it's basically the application of superposition principle.
Okay. So, audience, if you have any question, you can always post here on the window.
Yeah, if you have a specific question related to your problem or research, please send me an email. I can answer your question in more details in that case.
Yeah, and there is one more question here. Diffraction coefficient for conducting objects are available in literature, but what about dielectric materials?
We have a few small projects, graduate level projects about penetrable objects. Both high frequency asymptotics and our numerical multi-step approaches are applicable for both non-penetrable and penetrable objects. It is quite tricky, but applicable. If in that case, you have multiple regions where you have reflections, incident field, and refractions. In the examples I showed you in this presentation, we don't have refractions because the wedge is non-penetrable. When the wedge is penetrable, you need to focus inside the wedge also, and you need to include refractions. So in that case, we have incident fields, reflected fields, refracted fields, and diffracted fields. So you can still apply multi-step approach and discriminate them.
That was nice. And next question is, how do we decide that surface wave will get excited if we consider a grounded dielectric?
Could you repeat the question?
Yeah, how do we decide that surface wave will get excited if we consider a grounded dielectric?
Surface wave.
Maybe they meant like, how will we know like exactly the surface is excited if it is a dielectric?
Now, I'm not sure about method of moments, but if you use FDDT, it automatically creates or generates surface waves in the simulations. So the next important thing is how to distinguish or how to discriminate surface phase from the others. I don't have direct answer for this question, but it may be a challenge.
When there is a high cutoff frequency, which will be very high.
Yeah, but FDDT is general. So whether there is a cutoff frequency, whether there is a surface wave or cutoff waves or attenuating waves, FDDT generates all of them because FDDT is directly based on the discretization of Maxwell's equations. So whatever Maxwell equations handle can be handled by FDDT. So all the electromagnetic phenomena are there in FDDT simulations, but I'm not sure how you can discriminate surface waves from the others. I need to think about that. But it may not be easy.
Okay. So there's another question. Will hybrid methods help in diffraction analysis?
Yes. Actually, hybrid methods is good to extend the range of validity and range of application of limited methods. So if you combine, for example, high frequency asymptotics with FDDT, you extend the range of validity of both methods. And in FDDT, you need high memory and fast processors. So if you combine FDDT with high frequency asymptotics, you do most of the job with the mathematical equations, then you make it faster and more accurate to obtain the result. So if you have method A and method B, which are valid in certain regions, if you combine them, it will extend your range of applicability. So whatever you can do with method A and with method B will be combined.
Yeah. So the next question is, how do we measure the diffracted fields? Is it possible in anechoic chamber?
Yes, actually, it may be a good project. I'm looking for a young PhD candidate to do that, because in an anechoic chamber, by applying exactly the same multi-step procedure that I showed you in this workshop presentation, we can do the same during the measurements and measure the diffracted fields. So you measure total fields, then you know the incident field. You subtract the incident field from the total measured field, and you get reflections and diffractions only. You get rid of the incident field. And the next step, you get rid of the reflections, and you end up with the measured diffracted fields. If you have any PhD level researchers, and if you have anechoic chamber facility, that would be a nice project.
So there is another question, like in signal where incident pulse, reflected pulse, and diffracted pulse are shown, the reflected pulse and the incident pulse had the same phase. So won't there be a 180 phase change? And how to do the frequency analysis of the gated pulse?
Could you repeat the question?
Maybe
Incident
this
field
was
and
one of the
reflected.
slide which you had shown on incident pulse, reflected pulse, and the diffracted pulse. So
Yes.
they want to know, won't there be a 180 phase change? And how would the frequency analysis of the gated pulse?
It's exactly the same, but the incident and reflected pulses have the same phase or one type of boundary condition for hard boundary condition, because you have full reflections. But for the soft boundary condition, which means on the face of the wedge, incident and reflected fields becomes zero, so they have opposite phases. So sometimes the phases are equal, sometimes the opposite, depending on the boundary condition. But the procedure is the same. You just apply the Fourier transform and get the frequency response of incident field, reflected field, and diffracted field, because you subtract one from the other in the time domain. You don't need to worry about the phases of each incident, reflected, and diffracted pulses.
I think we have answered all the questions which were addressed by the participants, sir. And with this, I think it was a great insight where most of our audience were really happy. And even though being a virtual one, having a COVID situation, and we just feel we were just right in front of you, and you were there with us, and you gave us all the insight, and your knowledge was all shared with us. And it was just a great session, I can say. The workshop, a long workshop, since morning you were with us, and I would say, like, really would like to thank you for all the things what we had done, and it was a great session, believe, and thank you so much for being with us.
Thank you, Ashwin.
And most of your audience are really happy, and they are all thanking you for all your time here. And yes, because it's just the one way what we are concentrating here, we could not give both the side talk even for the audience, or else it would be too much mess with the audio. So that's the reason we have given the speaker and the panelists the voice, and others. Yes, I hope most of the questions what you people had, it's been conveyed and it's also been answered. And also the speaker has told you, like, you have any other questions, you can always mail him, and he'll be helping you in answering them. And yes, I would thank Professor Levent Sevgi and an eminent person, I can say, with so much experience and sharing a lot of things with us. It was really a great day, I can say, attending this workshop and sitting back on our couches and being with you. And thank you so much for sparing a lot of time and conducting this workshop on electromagnetic diffraction modeling and simulation. And thank you once again, Professor Sevgi.
Thank you. Yeah. See you in the future. Bye-bye.
Bye. And dear participants, we have other next paper presentations which will be happening from 1:30 p.m. IST. So I request all of you to join back with the same link, WebEx link at sharp 1:30, where we'll be having people presenting the papers. And you can just join 5 minutes before the event. And I've already shared the feedback link and also the Telegram channel, where most of the things are being uploaded there. We have even parallel tracks happening. So you can always make sure you attend any of the tracks of your choice. And we'll just have a lunch break back in our couches and then get back at 1:30. Thanks for attending this event. Thank you so much.